So I would like to hand over the stage to Henrik from Phoenix BioPower. Feel free, Henrik.
Thank you, Linda. So I'll start sharing my presentation here. There we go. First of all, thank you all for having me and for joining me today. My name is Henrik Båge, CEO and co-founder of Phoenix BioPower, and we are developing a new technology for high efficiency biopower. So why are we doing this? Well, as you all know, we need to do something about the energy production today, and we need to phase out fossil. Today, fossil power makes up around 2/3 of power generated, and it's primarily coal. And if we want to meet the targets of the Paris Climate Accord and the 1.5 degree, not only do we need to change the share of renewables in the energy in the electricity mix from about a quarter to 85–86%, we also need to double the global power generation capacity. So if we want to dial that down to some sort of annual numbers, that is, we need to add about 1,000 terawatt-hours of renewable power generation every year. That is an enormous number. And just to give you a sort of a grasp of it, it's like adding 3.5 UK every year or 1 US every 3 years to the global power generation system. So there is room for a lot of solutions to this. A big chunk of this will be provided by solar and wind. We all know that. These are fantastic technologies. I myself have worked 8 years within solar, so I know much about their benefits, but also a little bit about the drawbacks. Solar and wind are intermittent powers, so that means we will get increased volatilities, a little bit that Linda mentioned today about the capacity issue. We have that notably with rising prices, which this will need massive investment in grid infrastructure for transfer, but also storage solution, be it batteries, pumped hydro, or whatever, or things like that. And another consequence of this increased volatility in power generation is that if you're looking at a duration curve like this, when you have the cheapest prices to your right and the most expensive or cheapest hours to your right and the most expensive one to your left, we will see that variable renewables will harvest the majority of their power generation in the cheap end, whereas if you can plan your power generation, you will be able to harvest higher average market prices, and this has been proved empirically. And the more renewables variables we get into the system, this curve will shift, and we will see, as we have seen, negative prices, and that will increase, as well as extremely high peak prices on the other end of the scale. So our solution to this would be is basically a solution for plannable renewable power, so that we have a scalable technology, utility scale, that can be distributed throughout the energy system, like Europe, the entirety of Europe, not only just in Scandinavia. So what is it that we want to do? So we call our technology the biomass fired top cycle. So it's high efficiency biopower where we combine biomass gasification with gas turbine combustion, rather than the traditional steam cycle technology where you boil water to generate steam to drive a turbine. And what we see with this technology is that we can get a near double of the electrical efficiency from biomass. And as I said, we integrate the gasification with the combustion in the gas turbine so that we can recycle waste heat from the gasification process into the gas turbine. With the fact that we also introduce a lot of steam in the process, means that this is a cycle or a gas turbine which is 100% capable for hydrogen combustion should you need that for peak and shoulder operation. There are enormous amounts of waste energy from this process after the power cycle, which means that we can reach superior BECCS economics using waste heat to drive the CO2 stripper. And to sum it all up, this also gives us plannable renewable power for the decarbonized energy system. So if we want to dive a little bit down to the technology, how does it work? So we compare to your traditional steam cycle, we're using the same kind of fuel, low-grade biomass, wastes from forest and energy. We dry it, then we take it to a gasification and cleanup system. We take the gas back into the top cycle turbine where we generate the electricity, and then we have waste heat recovery, so we can get back steam from the process, and we can use that heat for heating and CO2 capture. So in the first steam part of this, we're using steam as a working fluid, so it works as an energy carrier between the gasification and the gas turbine, so that we can then recycle waste energy. So here we are working at very high temperatures. But then at the back end of the cycle with the fluid gas condenser, we can then use low temperature energy to drive the drying system, but also the CO2 capture or district heating system to basically utilize temperatures in the cycle from about 1400 down to 50 degrees, giving us a very high total plant efficiency, not only very high electrical efficiencies. We are now running a pretty aggressive development effort. We have so far invested a little over 6 million euros into this company. We are funded by public funding institutions. We have a good cooperations with Akademiska Hus. We have we have about 2,000 shareholders that are private investors, and we also have the support from Europe's premier clean energy investor, Innovenergy. We have a great site. I tend to call it Sweden's most beautiful building. It's a closed down coal-fired power plant at the center of KTH campus, where we do most of our testing. We are working with pretty notable companies throughout Sweden with our reference group. But this is a complicated development. So we are working with partners to drive the development of this technology together with KTH, TU Berlin, and RISE, to name it, but a few. We have and are conducting a number of pre-studies with notable companies throughout Europe. And we're now also doing a pre-study with the Zoryamash, just the logo there to the bottom right, which is a Ukrainian gas turbine operator who have experience in steam-injected gas turbine system. What we have invested, we have also secured upwards of 10 million euros in direct and indirect funding for this development effort in our next phase of our R&D. This is the founding team together with Michael, my CTO, and I. We basically run the daily operations of the business, but we also have Oliver Paschereit running our combustion engineering at TU Berlin, and Hans-Erik Hansen, who's the original inventor of the gas turbine technology. We have a pretty reputable board led by Mr. Stefan Jakelius and senior executives from different parts of the business, from banking and financing to gas turbine manufacturing. Funding, we raised 2.2 million euros a little less than a year ago. We have then, as I just said, we've secured around 10 million euros in funding from primarily the European Union for some of our development efforts. We are now a team of about 17, and we're looking to be north of 20 by the end of the year. And we will be raising somewhere between 7 and 10 million euros within the coming 12 to 8 months to accelerate our development effort. And we are also actively looking for industrial partners to partner up in the product and technology development of what we want to do. We do believe that we are an impact technology company. We had some friends evaluate us and to see how we correlate to the global goals, and they found that our technology can have a direct influence on 7 and indirect influence of 6 of the 17 global goals. So 13 out of 17 we think is a pretty good scoring. And with that, actually, I am done. I don't know how much time I've spent, Linda, but if there is any time left, I'll be happy to take any questions.
I think that was perfect in time. So I don't see any questions from the audience. You might still write them. We'll bring them up immediately if you can, or later.
Otherwise, you can just reach out to me directly through the chat or by mail. you have it here on the screen.
Yeah. And we also plan to share everyone's contact details in the thank you email afterwards. I have a question. Can we be used as input for this one? What type of materials?
Well, initially we're targeting forest residues, treetops, wood chips, and waste streams from the forest energy. We are also investigating agricultural wastes. We have looked deep into bagasse, which is from sugar production, but we're also looking into corn waste. So we know that forest waste is a sort of a scarce product outside of Scandinavia, Germany, and North America. But we see that in countries like India, there is ample access to different kinds of forest wastes. If we can go as far as straw, I don't know. It has to do with chemistry of the fuel.
Another one. What's the typical size of this? Who would be the typical customer? Is it
our first generation demo plant we are working on now would be around 25 megawatt electric in capacity. So that's around 50, and it will be operating in near 50% electrical efficiency. So that's about 50 megawatts of fuel. So that's sort of in Sweden, a mid-size plant, in continental Europe, a large-size biopower plant with an uptake area of, say, 60 to 80 or 100 kilometers, which is feasible in terms of from a cost perspective. So, and how much does that work? Well, in Scandinavian terms, this plant can provide district heating for about 5,000 single-family homes and about 50,000 households.
Great. Thanks a lot, Henrik. Very good.
Thank you. I'll stop sharing.